Camera, hello.
Alright guys, so we have our first 4 questions on the review, and we were going to find the amplitude and the period, and we're going to look at the form of a trig function with all of our info. We can have a sine bx minus c plus d, or a cosine bx minus c plus d for these two problems, where a is our amplitude and b is how we determine our period. And to do that, we need to take 2 pi over b, and that'll give us our period for each of these. So here I have a 3 out front where my a is, so a is here, and this is a 3. So for this one, my amplitude is 3, and then my period is 2 pi divided by 2, and that's just going to leave me with pi. So here's my period, and there's my amplitude for that one. For the next one, we have cosine of x. There's no number out front of the cosine, and there's no number in front of the x, so we can see both of those to be assumed as 1. Here I'm going to use the cosine this time, since, well, my trig function is cosine, and with this understood 1 here and here, my amplitude is 1, and my period is 2 pi over 1, which is just 2 pi. The next one's a little bit different. This time we have a damp on our cosine, and what that means is our amplitude is 1/2, meaning when we would draw this, instead of starting at 1, we're going to start at 1/2 and go on from there. So we have an amplitude of 1/2 that's above the x-axis and below the x-axis. You go 1/2. Here we're going to have a keep change flip situation for our period, because we're going to have 2 pi over 1/8, which is the same as 2 pi times 8. So our period becomes 16 pi. If you want to see that in action, go to Wolfram or go to Desmos. You can ignore this because we're not too worried about the period or the amplitude, but let's look at that period and see one complete cycle is going to take 16 pi units. So it's going to be really stretched compared to our parent function. And then question 4, we have it damped again. It's 1/8, so it's going to be really small, right? It's not going very much above or below the x-axis. On the printed form, it's kind of hard to see this decimal here, so some of you will have this as b being 1/2, and some of you will just have b as 5. I understand that's a limitation of the printout, not you guys, so I'm going to do this both ways. If you saw the period, sorry, here it's a decimal. You saw the decimal at 5, you know this is 1/2, so this is going to be 2 pi over 1/2. We keep change flip that, it's 4 pi. And if you really didn't notice it, and I saw that you did 2 pi over 5, I would accept that answer as well. But for now, or we can see here a little bit better defined, there is a decimal point there. Alright guys, let's look at this one now. It says construct and solve for all 3 angles and sides of the described right triangle where C is the right angle. So I'm going to go ahead and start by filling that in. Every capital C, capital letters denote our angles. It's going to get 90 degrees. That one was already given, that one's already given, that one's already given, and that one's already given. So now I'm going to draw one of the worst right triangles I've ever put up, so we can actually get it to close. And if I mark that as my right angle, then that's going to be AB. So now I still have triangle ABC, and we're good to go. Now for this one, we're kind of lucky in that we have 2 45-degree angles. So we know that this and this are congruent. And we happen to be given A is 12. So if little a is 12, because the little letters are the side lengths opposite of the angle that generates them. If this is 45 degrees and this is 45 degrees, then their opposite sides are congruent. And this is our special 45, 45, 90 triangle. And we know for that one, your two legs are equal to S, and your hypotenuse is equal to S times the square root of 2. So for this case, C, or little c, which is opposite our right angle, is just 12 square root of 2. Now, on the test, I didn't say exact answer for this one, so if you gave me a decimal, that's fine. I asked that you round to the nearest hundredth. We really want to stop using decimals at any time at this point in our career mathematically, because we want exact answers as often and as much as possible. All right, let's look at number 2. Just a second to wipe all this out. Now, something funny is going to happen here. 2 years ago, or even up until this chapter, we know that a triangle adds up to 180. That's not changing, but what we have now are more tools that'll do more for us, and now we have to actually see if these triangles exist with these given dimensions, and if they do, we can solve for everything. And what I mean by that is we can no longer just say there's 180 degrees in a triangle. C is given to me as 90, B is given to me as 75, so I can find big A to be 15. Now we can still do that. We can say A would have to be 15 degrees to satisfy the Polygon angle sum theorem, where we have 3 sides. So we know that 3 minus 2 is 1, and 1 times 180 gives me the 180 degrees for the interior angle sum. So 15 has to be our answer if this works, but we're going to see here that this one actually won't work. And what I'm saying by that is we know little a is 12, we know little b is 13, and a lot of the time, in the past, we would just go ahead and do 13 squared plus 12 squared equals, c squared, and we'd throw that down as our answer. But now we have the tools to do stuff like, well, here, this one's really nice. If I wanted to find this angle measure trigonometrically, I have this angle's opposite side and its adjacent side. And if I know the opposite and the adjacent, I can say that the tan, the inverse tan, or the arctan of big A is equal to the opposite over the adjacent. And then I can bring out my calculator. And if I don't get 15 degrees, because I've already shown by doing my geometry math that this has to be 15 degrees, I know we're in trouble. So let's do 12 divided by 13. And we have this decimal. And then if we go to trigonometry, second, because I want arctan, I get this angle is actually going to have to be, was it 47? I already lost it in my mind. 42.7. So for these legs to be 13 and 12 in this right triangle, this angle A must be 42.7 degrees. And I can see that these are not equal. And if this is 42.7, this can no longer be 75. So it is safe to say that this triangle does not exist as it's given to us, right? This angle cannot be 75 because we have shown that it must be, or big A must be 42.7, not 75. And some of you may be sitting there thinking, well, what is angle B then? Well, let's find out. If I come here for B, I'm in the same situation. I know the opposite, and I know the adjacent. So what is my inverse tan for big B? Well, it's 13 over 12, right? I changed the reference angle. It's tangent. They're just going to flip. We already knew that. Let's do 13 divided by 12. Now I have 1.083 repeating. Go back into my trigonometry section, hit second, and get inverse tan. And now I get 47.2, which looks like I would round it really, right? Let me see. Yeah, 47.3. Let's do that just to make it a little bit nicer for us. And here I can see that 42.7 plus 47.3 is going to give me 90, this 90, and now I have 180. So if these legs are 13 and 12, the angle cannot be 75 degrees and 15 degrees. Be ready for that on the test. All right, let's see the next one. And you're going to run into these problems most often when I leave one of the angles blank. You're going to want to be able to show me proof that this is not exactly what it appears to be. In geometry, could you have done this? Yes. And I said it in class, I'm going to say it again. We start all of our problems in geometry with assume or suppose. We're starting off with that. We'll call it a fantasy item, right? It's not a real triangle. We're assuming that it exists, and we're going to say, if it were to exist, these are the values that it must hold. We're now in pre-calc and going into calc. We need to be able to verify these and show exactly what their values are. So I come here, I know B is supposed to be 5, and this is supposed to be 90. So this one would have to be 85 degrees. And I know C, little c, from A to B has a side length of 365. So how can I go about finding the rest of this triangle and verifying whether or not it's true? Well, if I start with my 5, if I want its opposite, it is little b there. I know that this is supposed to be 5 degrees, and I'm looking for the opposite. I don't have its adjacent, but I do have the hypotenuse, so it's going to be b over 365. And this is opposite hypotenuse, so this is going to be sine of 5, which really means I just need to multiply both sides by 365, and that leaves me with b. So sine of 5 times 365, so hit 5, go to trigonometry, sine times 365, and I get 31.8. Now, does that answer make sense? Well, opposite of 90 was 365. 5 degrees is significantly less than 90 degrees, but it's like an 18th of it. And 5 degrees is generating a side length of 31.8. Now, how do I check that? Well, if I want to, I did round this one, so it's not exactly precise. So I'm going to use it to check, though, just because it's going to be more convenient. And if I don't get back 85 degrees, then we're in trouble, right? So how am I going to check to see how that should be 85 degrees? Well, I now know I have this here. I know its adjacent is 31.8. And I know the hypotenuse is 365. Ooh, I don't want sine there. I want cosine there. And what I don't want to do is this. This is the value I'm checking. This is going to be cosine of big A inverse is equal to 31.8 over 365. And what we want here is this to come out to be 85 degrees. If it is 85 degrees, we're good to go for the next triangle. So here I have 31.8 divided by 365. And then I'm going to do my second cosine. Ooh, we got 85.001. You can see how, oh, no, you really can't, can you? My screen's not set wide enough. All right, I'll put it over here. Oh, there we go. So we had it, that we're so close. So now I can't use my rounded answer. I need to go in here and I need to say that b is equal to this, and I need to say that inverse cosine of A is equal to 365 sine 5 over, right, that's just my adjacent side, over 365. Now some of you are going to say, hey, this will simplify, and we don't need to put all of that in, right? This is 365 times sine 5 over 365. So really what I need is inverse cosine of A is equal to sine of 5. So I'm going to hit 5 sine, and then I'm going to hit second trigonometry second cosine, and that's 85. See how this number here is close, but not the same as this number here. So plugging this in with the exact value shows me that this triangle is in fact true so far. Let me find the other values and I can keep checking them. Be ready for this on the test. I've been stressing exact values all year. This is where they're really going to come into play. So if I get back exactly 85 degrees, we're good to go here. This one works out so far. Let's find little a now. Let's go with bluish color. Little a is going to be, oh, I know the opposite and I know the hypotenuse to an exact value without using this. So let's go with that. So I'm going to have sine 85 is equal to a over 365. And that's just going to give me 365 sine 85 is equal to a. And if I bring that back up, 365 times 85 sine, these work, is equal to 363.6. Oh, you can't see it because I had to cut off part of the screen. But we have 363.6. Now we already know if I do cosine or inverse cosine of b, 363.6 over 365, we're not going to get an exact value, so we're going to have to plug in that. Go ahead and do that for me and see if you get back exactly 5. And if you do, we're in great shape. I'm going to go ahead and just put 85 here, and I'm going to write this as 365 sine 85. And you guys are free to check it. Now, number 4, I'm not even going to put up on the screen, or I'm not going to draw it out, because I can see here, well, I knew this answer was 12. This one was 12 square root of 2. Now I've given you that a is 12. I've given you that b is 12. If the two legs of a 90-degree triangle are the same, that forces these to both be 45 degrees. Because if I do 180 minus this 90, I'm left with 90, and I have to split it evenly, leaving me with 45, 45. And I can just reuse that rule. Same exact triangles, just different pieces of information for you to fill out. All right, let's clear this one off. It's going to take a second, and let's look at the next one. So now we're back in that position where we have to verify for number 5. We have a is 72 degrees. We do not know b. We know c is 90. We know little a, and we know little c, but we do not know little b, which means we're going to have to spend a few minutes here not only backing up, but also solving for little b, and then double checking that we found little b appropriately. Oh, it won't let me back up anymore. All right, let's erase it by hand. That's interesting. I've never had run out of backups before. All right. So here we have a is 72. We don't know what b is. We still know c is 90. Little a, which is opposite of big A, is 91. Oh, I didn't erase this. But we know now this is 182. So if I wanted to find, actually I have enough information right now to find b, in that I can do the inverse cosine of b is equal to its adjacent side over its hypotenuse. And I can plug that right in the calculator. And as long as I don't get an error, we are in good shape. Look how convenient that is. What's the inverse cosine of that going to be, guys? 60. And what does that tell us? This one's not going to work, is it? This b would be 60 degrees for these two values to exist. But I can tell you right now, well, you can tell me that a plus b plus c does not equal 180. And for this to be a true triangle, they have to add up to 180. So this won't close. This is not even a polygon. This is just 3 line segments, 2 of which AC and CB meet at 90 degrees. but they do not close. So we know that this does not exist. And now we have our last one. This one is interesting that B is 1. So one of our legs is 1. And we have a 36 and 54. That's 90 and that's 90. So this one's going to work. I'm not going to erase anything. I'm just going to do this. Associate them in the same pattern. A is 36. B is 54. C is 90 still. And little b is 1. So from here, I can see that I have B and its opposite, and I want its adjacent. So if I say tan 54 is equal to the opposite over the adjacent, I can see that this is just equal to, well, cotan 54 is equal to A. And if you're asking or wondering how I did that, if I just reciprocate 1 over A, I get A. And if I reciprocate tan over 54, or tan 54, I just get cotan 54. If you want to see all the steps, you can see that I would end up with A tan 54 is equal to 1, leaving me with A is equal to 1 over tan 54, which is just cotan. So let's go back to our calculator, and we want cotan of 54. So trigonometry. I need the 54 first, don't I? And that didn't work out for me. 0.726. So my little a is really small. Oh, we're not even on that triangle, so that doesn't help us. 0.726. Does that answer make sense? Well, 36 degrees is less than 54 degrees, so this opposite side better be smaller than 1, and it is. And then if I want the last piece, I could say that, I can use sine of 54, because it was given, is equal to 1 over c. And we're going to do the same thing, this same rule. C is now equal to the cosecant of 54, by the same reason that tan of 54 is equal to 1 over A was equal to cotan 54, and we're ready to solve for it. So bring up the calculator again, and we want 54 seconds, or no, trigonometry, cosecant, and we get 1.23, and that is a good thing because it's now our longest side. 1.23. So little c is 1.23 and little a is 0.726. So be careful. Some of these will not exist, and you can no longer go that old geometry route where you say assume or suppose this is an actual triangle. You need to use your trig to prove it. Alright guys, these were the most hated ones in class, I believe. I know we got stuck on them in a couple of the classes for almost an hour. So let's look over them again. I already wrote out we need all 6 trigonometric functions evaluated. And what we're going to do first is determine which quadrant do these two lie in, where secant is negative and sine is positive. Well, everybody's positive in the first quadrant, so that's not going to work with our secant value. Here, sine must be positive in our second quadrant, and secant would be negative, so this is definitely a possibility. What we're doing now is narrowing down how many answers do we actually need. I don't have a tan value here. Tan would have to be positive, and I can see here that only one of these is negative and both of these are positive, meaning tangent would have to be negative, so it can't be here. Oh, let me erase that circle off my negative sign. And here in the fourth quadrant, secant or cosine is positive, so secant has to be positive, so it can't be here. So I can only have an answer in quadrant 2 for this one. Now in quadrant 2, I'm going to have a negative x value with a positive y value. So that's going to help me determine where does this negative sign belong. The 17 or the 15? Well, immediately I'm going to say the 15 because I have positive sign here, but there's a tiny chance that we're going to have a double negative. Are we though? Absolutely not. Not for this one, but let's go through all the way to show it. So cosine of phi would be x over r, and we have secant, so we have now, well, let's do the whole thing, not skip anything. This would become r over x, meaning I have r as 17 and x as 15, and I need my x to be negative in this case. So now, if I break it down, I have 17, negative 15. All I need is my y value, and sine is y over r, so we have 8 there. And all I have to do now is plug in everything and chug along. Also, you can see here that this negative sign definitely doesn't go in the middle. It goes with the 15. Sine was given to us as 8 over 17. Let's go ahead and take cosecant for free at 17 over 8. I was given secant to be 17 over negative 15. So we get cosine for free out of that one. That's a 5. And now all I need is tangent. Well, for tangent, I just take sine over cosine, and that's going to give me 8 over 17 over negative 15 over 17. We're going to have 8 over 17 times 17 over negative 15, leaving me with 8 over negative 15. Put the negative in the middle on the top. It really doesn't matter now. And for our cotangent, we get that for free off of this one. And those are our 6 trigonometric values. Alright, now let's tackle the cosecant of negative x equals negative 5 and cosine of x is equal to the square root of 24 over 5. First thing I'm going to do, deal with this negative inside, and we know that sine of negative x is equal to negative sine, and that rule is going to hold true for its reciprocal. So if the negative can be moved out and placed in front of it, we're going to do the same with cosecant to start. So let me rearrange that so that we don't have to deal with it at all. And I'm going to do that by just erasing that and making it appear right here. Now that I have negative cosecant equals negative 5, I'm going to divide by negative 1, and now we magically have cosecant is equal to 5, which means we have sine at 1/5, and we still have cosecant at 5. And here we have, let me change the colors up on it for us. This is Y, this is R. Over here we have A, and we have R. Why did I put A when you know that's X? We're not doing geometry anymore. For cosine, we're going to have, well, it's given to us root 24 over 5, meaning secant is 5 over root 24, or if you want to rationalize it, 5 root 24 over 24. I'm not going to ever require you to do that because your calculator is going to do it for you. And we've already thoroughly discussed why it used to be convention that you had to do it right away every time. All right, so for tangent, I'm going to want sine over cosine. That one's not going to be too bad. That's going to be 1/5 over root 24 over 5. And you can pretty much see that's going to be 1 over root 24, or just root 24 over 24. I'll take either of these answers. I prefer this one because it's less work. So I'm going to go ahead and put that in there as 1 over root 24. And then if I flip it for cotangent, I get root 24 over 1, and I am done. Alright guys, sorry to have to do this, but I am going to speed run these just because, well, some of you guys know what's going on, and I'm just doing this because I have had a few requests to do it, and I don't want to leave anyone hanging. And since I wasn't there Friday, I want to get through it so you guys know how to do it. Here I have cosine of b, or beta, times tangent beta. Don't let these things throw you off. These are all just variables, no matter how weird they look. And we can treat them like theta, x, phi, whatever you want to do. But this is just going to be simply rewriting it as cosine beta times tangent's other form, or its quotient identity, because I want it in terms of cosine to see if I can do anything with it. I'm going to have sine of beta over cosine of beta. Here I can see that these will cancel, and this will then just be sine of beta. Let me put that there. And next I have secant alpha times sine alpha over cosine alpha. Well, secant is 1 over cosine, so I have sine times, well, that is backwards for alpha. So 1 over cosine alpha times sine over cosine leaves me with sine alpha over cosine squared alpha. And then I can ask myself, is there anything I can do there? Well, let's see. I have sine alpha divided by cosine squared is equal to 1 minus sine squared alpha. And that's really not going to do too much more for me off the top of my head. Let's see, we could break this up. No, we really can't. There wouldn't be a point in it. So yeah, I would stop right here. Give me a comment if you have a better one than that, or a further simplified one. I feel like there's something we can do, but for now, let's call it sine alpha over cosine alpha, cosine squared alpha. Alright, I'm not even going to mess with this one. This is 1 minus sine squared alpha, but this is sine to the first degree, so I'm not doing anything. I'm just going to write simplified. You don't always have to do something. Alright. Alright, here we have sine x plus cosine x all squared. That's the same as a plus b squared. So this is going to leave me with a squared plus 2ab plus b squared. So we have here for number 17, that is the expansion of that. And here we're just going to FOIL this one out. We're going to have 25 plus 25 sine x minus 25 sine x minus 25 sine squared x. These are gone. And I'm left with 25 minus 25 sine squared x, which means I can pull a 25 out, and I'm left with 1 minus sine squared. And we know that that's just cosine, so we now have 25 cosine squared x. Alright, let's knock these out. I've had a couple students ask me what's the difference between part A and part B of each of these. And that is both questions in A, or all of the questions in A for this section, require the sum and difference formula, whereas B is just a straightforward evaluate cosine of 240 and subtract the value of cosine of 0 there. So for a sum and difference formula for cosine, whatever this sign is here, when it moves out it changes. So I'm going to have this here as a plus, and then this formula for cosine is cosine cosine. Why isn't this working? And sine sine. This would be our u, this would be our v. So we're going to have cosine of 240 times cosine of 0 plus sine of 240 times sine of 0. And here we know sine of 0 is 0. It has no rotation off the x-axis. So that one is solved for. And we know cosine of 0 is 1. And cosine of 240 is 60 degrees off of 180. Meaning we have a negative 1/2 for this because cosine is negative in the third quadrant, giving me a final answer of negative 1/2. Now let's try this one. Cosine of 240 again is negative 1/2. And the cosine of 0 is minus 1. And that gives me a total answer of negative 1.5 or negative 1.5. So we can see those are very different. So we have to make sure we see that difference. And when those are cosine of 240 minus 0 is included as a single argument of the cosine function, we get a very different output than if we take two distinct cosine values and find their difference. All right, let's look at the sine one now because this one has something funny going on. And while I'm erasing all this, don't forget, if you're having trouble finding like denominators to do your radian version of these, just convert them to degrees. And then when you're done, convert them back. Don't give me any answers in degrees, but simplify your workload in degrees. Now we have a problem with this. There's no 405 degrees on the unit circle. And just like before, we used to do this on a lot of our tests. Find theta so that theta is between 0 and 360 when in degrees so that we can evaluate it on the unit circle. And to make 405 satisfy this, I'm going to have to subtract one full rotation, leaving me with 45 degrees. This is a reference. This is a coterminal angle to this, but 45 degrees is on our unit circle, so it's easier to work with. So let's rewrite this as sine 45 plus 120. And we know that our sine keeps this plus sign in between them, but they're off balance in that we have sine, cosine, sine, cosine, sine. So we have sine of 45 and cosine of 120. And then here we have cosine of 45 and sine of 120. So the operator stays the same, but the trig functions mix up with each other in between. So sine of 45, I'm going to go with the old rationalized version of it. Cosine of 120 is 30 degrees off of the 90 degree axis. Why are you doing that? So this means I'm going to have negative 1/2 plus cosine of 45, same exact thing, but this time we'll do it this way, and I don't know why, I just wrote it that way. And the sine of 120 is the square root of 3 over 2. So here we're going to end up with, I'm going to go ahead and do this as the square root of 2 over 2. This is going to be negative square root of 2 over 4. And this is going to become square root of 6 over 4. And now I see I have like denominators. So this can be simplified into one fraction. And that is my answer. Now on the test it says find the exact values. This is what you have to give me. If you don't give me this, it's not going to be worth any credit. Anything in a decimal will immediately be marked incorrect. Alright, let's find the height of this flagpole. This is our flagpole, this is our building. And I can see here that this 65 degrees has an opposite of F plus B. So I'm going to write tan 65 is equal to F plus B. Slap some parentheses around it so it's a single term. And that's my opposite, and my adjacent is 400, meaning I'll have 400 tan 65 for the height of the flag plus the building. And then I'm going to have tan 28 is equal to b over 400. So this becomes 400 tan 28 is equal to b. So I can now do some calculations on this, and 400 times tan 28 is 212 for my b value. Now I have 400 tan is equal to 400 tan 65 is equal to f plus b. 400 tan 65 is 857.8. And now I can substitute this b in, so I'm going to have f for the flagpole plus 212 is equal to 857.8. Subtract 212 from 857.8, and I get the flagpole is 645.8 feet tall. A bit ridiculous, but it's a math problem, so it's fine. All right, we got a sign on the roadway at the top of a mountain indicates that for the next 4 miles, the grade is 9.5 degrees. See the figure below. Find the change in elevation for a car descending the 4-mile stretch. So basically, we want to know this right here. That's our A. So we really have this triangle A. This is 9.5. And the hypotenuse is 4.5 miles. I know an angle, I know it's opposite, and I know it's hypotenuse, so I'm just going to say the sine of 9.5 is equal to 8a, over 4 miles. I don't know why I put a 0.5 there. Multiply both sides by 4, and the sine of 9.5 is equal to a. So let's see what that is. 4 sine 9.5. And I get a is equal to 0.66. And that might seem ridiculously small, but remember we're talking about miles. So over the 4 mile road at a 9.5 degree drop, they've dropped about 2/3 of a mile, which is perfectly reasonable.